Good morning dear students, myself Sachin S. Pawar and I welcome you to my 7th video on states of matter, gases and liquids. In our previous videos we have gone through various gas laws and the list of that all is there on your screen. We have learnt Boyle's law, Charles' law, Gay-Lussac's law, Avogadro's law, their mathematical forms. We have combined Boyle's law and Charles' law to get combined gas law. And we have combined Boyle's law, Charles' law and Avogadro's law to get the equation of state, also known as ideal gas equation. We have also deduced the value of R using STP conditions. We have used old STP conditions and new STP conditions. Here in the beginning I have taken new STP conditions and these are old STP conditions. New STP conditions 0 degrees Celsius and 1 bar, old STP condition 0 degrees Celsius and 1 bar. For new STP conditions we have three values of R depending upon what is given in the data. If the 8.314 joules per Kelvin per mole is the SI unit. If you know if the data has volume in liters and pressure in atmosphere, we can use this value as 0.0821 as the value of R. And if the pressure is given in bar and the volume is given in liters, you can have 0.0831 liter bar per Kelvin per mole as the value of R. Since we are having new units, oftenly these are used. But this is rarely used one where the value of R is obtained from the old conventions, that is 0 degrees Celsius at 0 degrees Celsius at 1 atmospheric pressure, and that is 8.2057 into 10 to the power minus 2 liter atmosphere per Kelvin per mole. That is not much use. We are going to use only these three. With this, let's continue with the combined gas law. Okay, combined gas law and ideal gas equation. So we have learnt ideal gas equation. Today we will go for some applications of one application of the ideal gas, that is derivation of relation between the density and molar mass of gas, density and molar mass of gas. This is the 3 marks question. They may say this question as it is, or they may say using ideal gas equation. Using ideal gas equation. So let us derive this. So we need a derivation of relation between density of the gas and molar mass of the gas. So we know by definition we know density D is equal to mass upon volume. So if you just say M as the mass and capital and V as the volume, then density is equal to M upon V. We have got one equation. Density, okay, so I have got an equation. Density is equal to, by definition, density is equal to mass upon volume, which is okay. Now I have got this equation. I have a density term. Now I want a molar mass term. You know, molar mass by definition is the mass of 1 mole of a gas, that you have learnt in your PUC first year unit number 1. It is the mass of 1 mole of a gas. Okay, you have learned that. So you know mole means, you can say number of moles term you have used in this. So do we have any relation where number of moles are there? Yes, we have an equation that is called as the ideal gas equation. So ideal gas equation is PV is equal to nRT. We have an equation PV is equal to nRT, where N is number of moles, and the number of moles and molar mass are quite related by equation which you already know, you have learnt it in your PUC first year unit number 1 as number of moles of gas N is equal to mass upon its molar mass. Mass upon its molar mass. Let it be M upon capital M, where capital M stands for molar mass. Then if you substitute this in this equation 2, equation 2 implies PV is equal to M upon capital M into RT. This is equation number 3. Now I have got an equation with molar mass in it, and I have an equation with density in it. Either I have to make some necessary changes so that I can substitute this in this equation, in first equation, or substitute first equation in third equation, so that I can have a combination of density and mass in the same equation. That I can do by simple observation. In this equation we have mass upon volume in the right hand side. So can we bring that in this equation 3? Yes, we can bring. So equation 3 implies, see what equation 3 implies. Equation 3 implies, see, I'll just bring mass upon volume on the right hand side and rest all on the other side. So it becomes P into M upon RT. So I'll get equation number 4. So you just see in equation number 3 I have just transferred M to the left hand side, P to the I have transferred V to this side and rest all to left side, and we have got this equation PM upon RT is equal to MV. Now if you just observe equation 1 and 2, equation 1 and 4, M upon V, the right hand side of both these equation is same. So by observing equations 1 and 2, the observation of equations 1 and 2 implies, since right hand side are equal, left hand sides are equal, density is equal to PM upon RT, and I have got a relation between density and molar mass. And it's clear that density on left hand side in the numerator, molar mass on the right hand side is in the numerator. Therefore density is directly proportional to molar mass, and this is the relation between density and molar mass. Density of the gas is directly proportional to molar mass of the gas. This equation can be used for calculating the density, provided you know the pressure and temperature at which we are carrying out the reaction, and the R value and the molar mass. In competitive exam, we should also use this as a hint to solve some problems. Say for example, if you have been asked, out of oxygen and nitrogen, which has more density? Suppose I have taken two gases, oxygen and nitrogen, and if they ask you which of these gases have more density, then without calculating also we can predict which gas has more density. Like for example, oxygen, the molar mass of oxygen is 16 plus 16, that is 32 grams per mole, and that of nitrogen is 14 plus 14, that is 24 grams per mole. And it is very much clear that molar mass of oxygen is greater than the molar mass of nitrogen. And since density is also proportional to M, we can clearly say that the density of oxygen is greater than the density of nitrogen, right? Great. So here, based on molar mass, or just by looking into the molecular formula of these, we can predict whose density is higher and whose density is lower. And this is the application of this equation. Okay, with this, let's move ahead to the next statement, that is Dalton's law of partial pressure. Dalton's law of partial pressure. Okay, what is this Dalton's law of partial pressure is? The Dalton's law of partial pressure, the statement goes like this. The statement is the total pressure of a mixture of non-reacting gases, total pressure of a mixture of non-reacting gases is equal to sum of the partial pressures of the individual gases present in the mixture. Okay, let us understand this. Suppose we have a mixture of two non-reactive gases. Now this is very important. Before I go further, this law is applicable to that mixture which has non-reacting gases, because see, if the two gases are reacting, they will combine to form the third gas, and both these two gases will disappear to form third gas. In that case, these become reacting gases. So in that case, these gases lose their individuality, existence, and that's why we cannot apply it to the reacting gases. They should be non-reacting gases. Okay, now here if I take the mixture of non-reacting gases, say gas 1 and gas 2, then they say that in that mixture, suppose I have a container, in that container I have gas 1 and gas 2, then they say that the total pressure of that mixture, the total pressure in this container is equal to the pressure of component 1 and pressure of component 2 and so on. If there are many gases, then I can go on writing the total pressure is sum of the partial pressures of the individual gases. This is the statement of Dalton's law of partial pressure. Okay, now this statement can be used like this. The statement can be used in synthesis of gases like this. The synthesis of gases. Okay, so significance of this Dalton's law, we shall see. Significance of Dalton's law. The significance of this statement. The significance. Okay. Now, the significance of this Dalton's law is well understood when you see the preparation of different gases, preparation or manufacture of different gases, manufacture of particular gas, say hydrogen gas, nitrogen gas, and so on. The preparation is done usually in this format. Here in the mixture, here what we do is some reacting mixture is heated in the container, and that the reactions gives some gas particles. These gas particles being light in weight, they bubble out of this, and they are made to bubble out through this tube, and they are collected in a gas jar which is inverted over a container containing water. So as the bubbles are formed, these bubbles will move out, and they collected at the top of this by downward displacement of water. So here you see there is a layer of water and the entire gas is collected here. So when you see the gas particles here, these gas particles, the gas collected here is not alone. It's not alone. It is a mixture of the gas and water vapors. And remember, the total pressure of this gas will be equal to, so total pressure, if you measure here, then the pressure here will be equal to pressure of that gas plus pressure of the water vapors. The pressure of the water vapors. The pressure of the water vapors is known as aqueous tension. It's known as aqueous tension, and its symbol is F. Its value is fixed at a specific temperature, and in the literature at various temperature the values of F are known to us. So this becomes a dry gas, and this along with water becomes a wet gas. Okay, so the pressure of dry gas will be P minus F, and that's why the Dalton's law becomes useful for determining the pressure of dry gas, because of Dalton's law only we can say that the pressure of the wet gas, that is total pressure, is equal to pressure of dry gas plus pressure of water vapors. And to get the pressure of dry gas, we subtract the aqueous tension at a specific temperature from the pressure which we have measured. Okay, that is the wet gas. So this equation becomes useful. We will be using this equation in some problems. So this is the significance of Dalton's law of partial pressure. Let's move on to the application of Dalton's law, and the application of Dalton's law is the derivation of relation between partial pressure and mole fraction of the gas. Partial pressure and mole fraction of the gas. Okay, so we want a relation between partial pressure and mole fraction of the gas. Now the term partial pressure is coming in the Dalton's law. Therefore Dalton's law for mixture of two non-reacting gases say 1 and 2 is total pressure equal to the partial pressure of the first gas and partial pressure of second gas. This is equation number 1. I'll write it. This is Dalton's law of partial pressure. So we have got one equation containing partial pressure. Now we want an equation containing mole fraction. Do you know what is mole fraction? Yes, we have learned this mole fraction concept in unit number 1 of PUC first year. And by definition, the mole fraction is defined as the number of moles of the component upon the total number of moles present in the solution, present in the container. Suppose we have N1 number of moles of first gas and N2 number of moles are the number of moles of gases 1 in the container of number of moles of the components 1 and 2. Then the mole fraction of the first component will be equal to number of moles of that first component divided by the total number, and total number is, since there are only two gas particles here, the total number of mole will be number of moles of first gas plus number of moles of second gas. This is equation number 2. So I have got mole fraction of the first component as N1 upon N1 plus N2. Now I have got an equation where we have mole fraction term, and we have an equation where the partial pressure term is there. Now I need to correlate these terms, correlate these. Now to correlate, I need to use one more equation here, because here X and P are related by number of moles. Therefore I need to use of equation where the number of moles are there, and that is the ideal gas equation. So for according to ideal gas equation, that is PV is equal to nRT. We know for components 1 and 2 of the mixture, the pressure, the partial pressure is P1 for component 1 into V, volume remains the same because the container is not changing its volume, is equal to number of moles of that component into R into T. So here N1 becomes P1 into V by RT. Okay, so and for component 2, it is P2 into V is equal to N2 into RT. Here volume and here the volume, temperature and R value are fixed, because here we are taking the mixture of gas in a container which is not changing its volume, and at a fixed temperature, and the value of R is also constant, as you know it as 8.314. so N1 I have got this. Similarly N2 I will get it as P2 into V by RT. Okay, similarly for the mixture of the gas, the number of moles is N1 plus N2, because there are two components, the total number of moles is N. So here the equation becomes P total, volume is same, equal to N1 plus N2 into R into T. That is N1 plus N2 is equal to, that implies N1 plus N2 is equal to, N1 plus N2 is equal to P total into V by RT. Okay, so if here in this equation, now see I have equation number 3 if I say, and if I say this as equation number 4, then if you divide equation number 3 by 4, or I'll say equation 3 divided by equation 4. See, I have equation 2 N1 upon N1 plus N2. So if you just get equation 3 and 4, substitute in equation 1. If you substitute equation 3 and 4 in equation 1, I'll get mole fraction is equal to N1 is, so this implies, so equation 2 implies equation 3 and 4 in equation 1 implies, okay, so it implies x1 is equal to, just see, x1 is equal to N1 is P1 into V by RT upon N1 plus N2 is P total into V by RT. and here the V by RT is common in numerator and denominator, therefore I can easily cancel it. And this becomes, and that implies P, that implies x1 into P total is equal to P1. So I have got the relation between the partial pressure and the mole fraction. So the partial pressure and the mole fraction is, the relation is the partial pressure of the component is equal to the product of mole fraction of that component into the total pressure of the gaseous mixture. And this gives us the relation between partial pressure and mole fraction of the gas. And this all is the gas laws and applications of gas laws. In today's class only this much is there. In next class we will go with problems on these gas laws and some more applications of these laws that we shall see. I'll stop here. Thank you.